caused by cosmological constant with negative pressure. The corresponding energy density for lambda um, is um, is in disagreement with the field theoretic estimate by 120 order of magnitude. So various attempts are made to um, modify GR in IR. We are looking into one such modification by assigning mass to graviton. So the quest for a complete theory of gravity mediated by massive spin to particles known as graviton started in 1939 with Fritz and Pauli. However, the theory had a number of pathologies. The massless limit did not recover to GR. Also there are some ghost degrees of freedom. Until recently, in 2011, the interest in the spin to massive gravity was rekindled with the introduction of DRGT theory, named after the creators Diram Gabadadze and Tolley. So this theory successfully removes ghost in all order. To construct the mass of graviton, we need two metrics, namely the physical metric g mu nu, and which couples to matter, and the fiducial metric f mu nu. The fiducial metric is constructed from the Stuckelberg field, which helps to restore the covariance of the theory. In this analysis, we have looked into an extension of the theory by a scalar field known as quasi-dilaton. The quasi-dilaton helps to establish stable, self-accelerating, homogeneous and isotropic cosmological solutions. This is the complete action for the theory, which consists of the gravity, the contribution from gravity sector, the massive gravity contribution, and a general matter Lagrangian. And the massive gravity Lagrangian is in the familiar form. It's made up of the contributions L2, L3, and L4, and they are constructed by tracing various powers of matrix K. K is a special combination of the physical and the fiducial metric. So here we also introduce this parameter x, which will be useful for our future analysis. So to find the Einstein-Hilbert action, we have resorted to ADM formalism. In this formalism, the metric is split into lapse and the shift, and the Einstein-Hilbert action is written in three-dimensional Ricci scalar and a combination of extrinsic curvature. By decomposing the action in this way gives us an advantage of identifying the surface terms which appear as total derivatives, and we can either drop them or explicitly cancel them by adding boundary terms. So from now on, we will consider conformal time tau by changing the lapse of the metric as the scale factor. This is the background equations we obtained from the action. Two Friedman equation in conformal time. They have distinct contribution from the matter and massive gravity contribution. And we also have two other background equations, Stuckelberg equation of motion and quasi-dilaton equation. The Stuckelberg field, we have chosen a gauge so that the spatial part of the Stuckelberg field is same as the unitary gauge value, and the 0th component is parametrized with a function f of tau, and the small n here represents the effective lapse function for background Stuckelberg metric. So for a general matter Lagrangian, we can find the energy momentum conservation equation. So this is the continuity equation in zeroth order, and combining the two Friedman equation, we obtain a condition on the background value of the massive gravity parameters, which is valid for all times. Looking into this equation, we can find two branches of solution. So in one of the analysis, it is shown that the branch one is more interesting for cosmological observation. This is the plot we made for the Hubble parameter in branch 1 and compared with lambda CDM. So now for the scalar perturbation, um, we have 8 scalar perturbations in total, from among which 2 we can gauge away using the diffeomorphism invariance. So we have introduced one scalar perturbation in matter sector, 4 perturbation in the physical metric, 2 perturbation in the Stuckelberg, and 1 perturbation in the quasi-dilaton field. So here the metric physical metric in ADM form is given in this way, and these are the perturbation in physical metric. So we have 4 functions: phi, e, psi, and e. So for now, for our growth of structure analysis, we have considered the conformal Newtonian gauge, where we have set B and E to be 0. The advantage for choosing this gauge is that the metric function phi and psi coincide with the gauge invariant quantity. This is the equation metric in conformal Newtonian. However, the Stuckelberg fields are not dimensionless; they have finite dimensions, whereas the phi and psi are dimensionless. So we have rescaled the Stuckelberg fields with the mass of the graviton. So this is how we have rescaled the Stuckelberg field. So this is these are the equation of motions we have obtained from second order action. So the scalar perturbations I have introduced in our previous slide, substituting that back into the action and expanding the action up to second order in the scalar perturbation, we obtain the second order action, and varying the action with the physical metric, fiducial metric, and the quasi-dilaton field, we obtain the perturbed equation of motion, and the continuity and the energy momentum conservation equation gives the continuity and the Euler equation. Since we are mostly interested into studying the evolution for the matter over density delta, we are making following assumptions. So we are looking at the subhorizon level, and we are also where the wave vector k is much bigger than the Hubble and the mass of the graviton, and we are also making the quasi-static approximation, where we are approximating the time derivative for the perturbation to be Hubble times the perturbation. So here, combining the perturbation equations with the Euler and the continuity equation, we have derived a single equation for on the a single evolution equation for the matter over density, and the modified Poisson equation is, and this is the modified Poisson equation, which has a parameter mu, and the ratio of metric potential phi and psi is parameterized by eta. So in GR, mu and eta should be equal to 1. Any departure from that value would potentially suggest a new theory. The growth rate equation, evolution equation, we can write that in terms of the growth factor, and taking the derivative of the growth factor, we can have another interesting quantity, the growth rate f of tau. So this is our result. In branch 1, we have a large expression for mu and eta in terms of the massive graviton, scale factor, and the quasi-dilaton field. So we have found mu to be diverging with the matter density estimate from lambda CDM. This could potentially mean um, the over density going to zero. So for our preliminary analysis, we have slightly increased the matter content, the value for the matter content, to get rid of the divergences. For branch 2, however, mu and eta, we found it to be 1, uh, but the equation for the growth rate is same as what we get in GR. The form of the equation is same as in GR, but the Hubble constant is now modified by the mass of the graviton and and uh, and other parameters of the theory. So these are our preliminary plots for eta and mu in branch 1. So eta is 1, identically 1 for GR, and both eta and mu. However, we have slightly different results. And this is our plot for the linear growth factor and growth rate. We have used slightly increased value for omega m, the matter content, and we have chosen the ratio of the mass of the graviton and Hubble parameter to be 10 to the power of -3. This is our ongoing analysis, and we are trying to check whether the perturbations we have considered are healthy or not. So for this analysis, we have particularly focused on matter as a scalar field given by chi. So the matter Lagrangian is given this way, and the background continuity equation we have obtained, and the gauge freedom we have chosen to be E equal to 0, and the perturbation for the matter field equal to 0. Also here, I would like to acknowledge that we have a discussion with Dr. Gundusulu for this matter field, and we have significant discussion with him. So this is a walkthrough on how we eliminated the non-dynamical degrees of freedom. So the perturbation phi and b appeared as a Lagrange multiplier. So we could solve that as constraints. Inserting back phi and b into the action, we obtained action in 4 perturbations: psi, pi 0, pi l, and delta sigma. Then we defined 2 orthogonal combination to find the Bulwer-Desser degree of freedom. So this is our expression for the orthogonal combination. So among between these two, we found delta sigma tilde is the Bulwer-Desser degree that did not have any kinetic term. And finally, substituting the solution for delta sigma tilde, we have an action in psi, pi 0, and pi l, which are all propagating degrees of freedom, and we obtained their 3x3 kinetic matrix. So to check whether we have positive eigenvalues for the kinetic matrix. We are we are testing these three conditions. So in for branch one, under subhorizon approximation, the matrix element K11 corresponds to the eigenvalue for this is exactly same as the curvature co-moving curvature perturbation eigenvalue from the inflation, and the determinant of K22 is given by this, and we are still trying to. So the full determinant of this matrix is a very large expression for the background quantities. So we are still trying to simplify that and find condition for positivity of eigenvalues. So here I would like to summarize our results. So we have studied DRGT theory in presence of matter with scalar perturbations. So we have looked into branch one, which shows interesting properties for cosmological observation. So still now in our ongoing study, we are looking at the conditions for positivity of the eigenvalues in branch one. We in this branch we have solved for growth rate and growth factor for matter perturbations, and we have found that mu the parameter mu was diverging with the matter content predicted by lambda CDM. So uh, to eliminate the divergence, we have slightly increased the matter content. So for our future study, we would like to use galaxy survey data to constrain the parameters more tightly. Thank you.
Thank you very much. Thank you for results that shared with us. And any question? Okay.
As the helicity zero mode, or there is some diagonalization which converts into one mode which is more effective than the other?
We are basically looking into the scalar perturbations. So we are interested in the helicity zero mode.
Thank you.
Thank you to all the participants and professors and the lecturers that were with us. I also thank Dr. Matavalli and Sopan and Ali that help us in every step. And I hope to see you all again next year in next conference. And this is
Thank you to the organizers, and all the best.
Thank you. Thank you very much. Thank you. خداحافظ.